Hello and welcome back to math class. On to chapter 3 of grade 12 calculus, derivatives and their applications. We'll start with higher order derivatives and a related concept, velocity and acceleration. Concept, higher order derivatives. When the derivative of a function is itself differentiated, the result is a new derivative, called the second derivative. So if the first derivative is the rate of change of the function, then the second derivative is the rate of change of the rate of change of the function. Yes, the rate of change is the second derivative. This itself could be differentiated to find the third derivative, and so on. Notation, the second derivative can be denoted in a few ways. Y double prime, f double prime of x. Now I put in here the fifth derivative, so f, the fifth derivative of x, d squared y by dx squared are a few of the notations used. Here's an example, find the first three derivatives. Well, it's really pretty simple. Differentiate the first one, which we know how to do. Now this is a simple example. Sometimes they get increasingly complex. So we'll differentiate the function and then differentiate the derivative to get the double prime, the second derivative. Here we have 12x squared minus 30x plus 8. And then differentiate this and we have the third derivative. It'll be 24x minus 30. The concept isn't deep, but sometimes these second and third derivatives can become quite complex. There is software available that will do it for you. Software where you simply type in, I want the 27th derivative of the following, and out it comes in about 2 seconds. Example, find the first two derivatives. Okay, there's y. Y prime is top thing prime times the bottom thing minus the bottom thing prime times the top thing over the bottom thing squared, and simplify. And we have the first derivative, negative 2 over x minus 1 squared. Going for the second derivative now. Now this example brings up a point. Consider what it is that we have to differentiate. The numerator is not a function of x. It's just the number negative 2, a constant term. So while it is possible to use the quotient rule here, it's not necessary because the numerator is not a function of x. But it is possible, so we could do it that way. Y double prime is top thing prime, which is 0 times the bottom thing, minus the bottom thing prime, which is 2 times x minus 1, times the top thing over the bottom thing squared. Now the left part of this just disappears because it's 0 times something, and the right part simplifies somewhat to this. And we have some canceling happening here. X minus 1 is a factor of both numerator and denominator, so it reduces to that. My suggestion would be, if the numerator is not a function of x, but a constant term, possibly consider rewriting this thing that needs to be differentiated as negative 2x minus 1 to the minus 2. And then when you differentiate, this minus whatever it is, in this case 2, just jumps out in front as a factor, and this will become 4 times x minus 1 to the minus 3. 4 times x minus 1 to the minus 3, and then this factor can be placed on the bottom. And of course you get the same result. Concept. Motion of an object relative to a point. Examples of this. A ball or an object projected vertically straight up, like a cannonball shot up or something of that nature, or possibly dropped from a height. It's motion of an object relative to a point. And if it were, in the case of the ball shot straight up into the air, the thing that it is relative to would be the ground. The point would be the ground. Another example of this concept would be an ant crawling along a clothesline relative to a clothes peg on the clothesline. What we do is superimpose a number line over the clothesline, and that clothes peg will represent the 0 number. And anything to the right is positive numbers, and anything to the left is negative numbers. They are one-dimensional motions. So in order to change directions, the ball, ant, or particle must come to a stop, i.e. its velocity has to reach, for a moment, it has to be 0. The ant has to stop, turn around, and then come back to change direction. So very quickly here, the position or displacement function is s of t, s meaning displacement. I think s stands for space between the object and the reference point. Could be h of t, where h still stands for the displacement between the object and the reference point, being the ground. Velocity is the rate of change of this displacement, so it's s prime of t. Velocity is s prime of t. Rate of change of space with respect to time, ds by dt. And the acceleration is the rate of change of the velocity, so it's the rate of change of rate of change. So it's the second derivative of the space function, or the displacement function. We just have to keep in mind, velocity is the first derivative, acceleration is the second derivative, or the derivative of velocity. Example, the motion of an ant crawling along a clothesline relative to a clothes peg is given by an equation. And t is in seconds, and s of t is in centimeters. A. What is the ant's velocity after 1 second or 5 seconds? Well, we'll need the velocity function. That's easy to get. It's just the derivative of s of t. Easy to do. And now simply sub in a 1. After 1 second, sub in a 1. Do the math, very simple. And after 5 seconds, sub in a 5. Do the math, very simple. In the first case, after 1 second, it's moving to the right. Because its velocity is positive, it must be moving to the right. And after 5 seconds, it must be moving to the left, because its velocity is negative. So there must be a point in between 1 second and 5 seconds when it came to a stop. In other words, its velocity must have been 0 at some point. When is the ant momentarily stopped? Well, I think we know it's between 1 second and 5 seconds. When? We have to set velocity equal to 0 and find out at what t was v of t 0. So there's our function, factoring. So t equals 2 or t equals 6. The ant is stopped at t equals 2 seconds and t equals 6 seconds. Where was it when it stopped? Now here's the thing in calculus, there's a lot of places to sub things. We have to think about it. What are the positions when the ant is stopped? We'll take t equals 2, which is a time we know it was stopped, and we'll have to sub it in to not the velocity, we'll have to sub it into the displacement function, which is that original function reprinted here. Subbing in 2, and the math is really simple. The point of the exercise is to realize you have to think about where you're substituting things into. And it stopped at 6 seconds, so let's sub in s of 6, put it in again to the displacement function, do the very simple math. And it looks like it was back at the origin. At s of 2, it was 32 to the right, and at s of 6, it was back home at the clothes peg. D, when is the ant moving in a positive versus a negative direction? Well, here's the graph of its displacement function, which we know to be a cubic, and we know that cubics do look like this. And this is what its graph looks like on the graphing software. The ant is moving in a positive direction when the derivative of this cubic is greater than 0. Then the ant is moving in a positive direction. I've made a corresponding grid down here on which we'll put the velocity function. Note, this is an upward-facing cubic. It's going off to infinity, to the right. And we know that its derivative will therefore be an upward-facing parabola. Because the derivative of a cubic is a parabola, witness the derivative of t cubed is 3t squared. And this particular parabola is going to have its zeros, its x-intercepts, happen whenever there is a horizontal tangent on the cubic. And so that'll be a 0 here at 2, and another 0 here at 6, because there's a horizontal tangent at 6. And there it is. We know this is the velocity function, and there's the graph of it. The derivative of this cubic, with zeros where there are horizontal tangents. An upward-facing parabola, because this is an upward-facing cubic. And just showing the factoring again, and yes, in fact, it's going to have zeros at 2 and at 6. And for it to be moving in a positive direction, the entire parabola must be greater than 0, because we want the velocity to be positive if it's moving in a positive direction, which means to the right. When the graph of the velocity is below the x-axis, then the velocity is negative, and the ant moves in a negative direction, and vice versa. So between 2 and 6, the y value of the velocity is beneath the x-axis. So therefore, between 2 and 6, its velocity is negative. And so between 2 and 6, it's moving to the left. The ant moves in a positive direction when t is between 6 and infinity, because between 6 and on to infinity in the x direction, the y value is positive for that interval. And it's also positive from negative infinity all the way up to 2. So from x equals negative infinity, which is over here on the left, all the way up to an x value of 2, this blue line is above. And so for those two intervals, the ant moves in a positive direction as opposed to the ant moving in a negative direction between 2 and 6. And so we study the velocity function to make statements about the direction of the ant's motion. Anytime we see the curve below the axis, we know that the ant is moving to the left. Determine the position of the ant after 10 seconds is easy. Take the displacement function, sub in 10, do the very simple math, and we have s of 10 equals 160, and we're ready to answer, well, the ant is 160 centimeters to the right of where it started because this is a positive number. And now find the total distance traveled during the first 10 seconds. Here's a diagram of its motion. There's the function. When t is 0, it was at s equals 0. And we know that at t equals 2, it stopped. And its position was 32 seconds. We figured that out from before. And then at t equals 6 seconds, it was back at its starting point. And we just figured out at t equals 10 seconds, it had traveled out to 160. So to get the total distance traveled in the first 10 seconds, we'll have to take 32 plus 32 plus 160. Typical velocity and acceleration type questions. Okay, the displacement curve is given. This is displacement. The displacement curve. It looks like a parabola. It opens down. It's y equals s of t. Sketch the velocity. Well, the derivative of this. Well, we know the derivative of a parabola is a line. Witness y equals x squared, so y prime equals 2x. And this is a parabola that opens down, so the line will slope down, and it will have a 0 where this function has a horizontal tangent. associating zeros with horizontal tangents. Horizontal tangent here, the derivative has a 0, and it's a line that slopes down through an x-intercept of -2. Y equals v of t, sketched. And the acceleration curve will be the derivative of this velocity. So if this is y equals mx plus b, then its derivative is the slope, y equals m. And the slope is drop 2, run 1, drop 2, run 1, -2 over 1, so -2. Y equals -2. The acceleration function, the green line. Some more exercise in this. The displacement curve is given. Sketch the velocity and acceleration. Well, this is an upward-facing cubic. The velocity, its derivative, will be an upward-facing parabola. And it will have zeros where we see horizontal tangents here. Horizontal tangents occur at these mountain tops or these valley bottoms. So right about there, I expect to see a 0. An x-intercept on the derivative. And right about there, I expect to see a 0 on the derivative. And I expect to see a parabola that opens up. Y equals v of t. And the acceleration curve will be the derivative of this parabola, which we know to be a line. And this line will have a positive slope because this is an upward-facing parabola. And it will go through, let's see, it'll have to hit the 0 when this has a horizontal tangent, which is right there at the number -3. And there's the acceleration curve, which is actually a line. One last example, the velocity curve is given. So in this case, the velocity is given, not the displacement function. It says sketch the displacement function and the acceleration. Well, if this is the velocity, the acceleration must be the derivative of velocity. And so it must have a 0 where this has a horizontal tangent. So it must have a 0 right about there, and it must slope down because this is a downward-facing parabola. So this is a reasonable sketch of y equals a of t, taken straight from the velocity function. And now the challenge. Given velocity, which is this parabola, we have to answer the question, what curve, when differentiated, turns out to be this? Because this is velocity, and it's the derivative of displacement. So displacement, when differentiated, turns out to be this. Well, this has zeros right there and right there, so there must be horizontal tangents in the cubic. And since this parabola opens down, the cubic must be one of those downwards facing ones that goes off, that runs away to -infinity. And so I would expect to see a cubic coming down and somewhere having a horizontal tangent right in line with this and a horizontal tangent in line with that. Something like this, perhaps. A horizontal tangent in line with this 0, and a horizontal tangent in line with this 0, and a downward facing cubic.